Okay, so it's been a while. Let's kind of talk through a couple examples. Why don't you everybody click and close, have a look up here. Let's go through this one step by step. Um, I want to take. I know this. We've already spent some time on this, but we got interrupted by break, and I still want to take at least a couple days to kind of work through some of these with you. This is it's such a big topic in calculus. It's if you get related rates pretty well, then a lot of other stuff that's coming down the pike just seems like it's not as big a deal. Okay, so what are we going to do here? What's our first step? I guess we want to try to interpret this. We have a graph. We want to find the rate of change of the distance between the origin and a moving point on this graph. So you could visualize this as though there were a piece of wire that were bent in this parabolic shape and there's a bead sliding along the piece of wire maybe, right? That represents the point. Okay, they give us an equation of the parabola, of the function, just x squared plus 1, and they tell us dx dt equals 2 centimeters per second. So what does that mean? What's dx dt? X dot. Okay, we could call that x dot. What does that mean though? What does that mean in the context of this problem? The rate that the point is moving or the bead is sliding? Not exactly. It's related to that's what we're trying to find, isn't it? If we were to think about this as being a bead, and let's say here's another point that we put a tack in the origin, and we've got a piece of string that's connecting the bead and the tack. Really, all we're doing here is we're just deciding like maybe there's a spool of string on this bead. It's wound up around the bead. As the bead is sliding along the parabola, we're trying to ask how fast is that distance changing would be the same thing as saying how fast are we letting out string, right? Everybody agree with that? Does that make sense? How fast is the distance changing, right? The rate of change of the distance. We could call that distance, let's call it S. A lot of times we do that if we're talking about a position or a distance. So that's going to be S. What are the coordinates of the origin? 0, 0, and those are constant, aren't they? Right? Those are not changing. So the coordinates of that point are 0, 0. Now, what about the coordinates of this point? Are those constant or variable? They're variable, aren't they? So I want to be able to assign some variables or symbols to those. What could they be, do you suppose? I could call them A and B. Maybe more easily, I could call them X and Y. Why not, right? X and Y are variables, and the rate at which those variables are changing affects the rate at which the distance is changing. Everybody agree? Okay. All right. Okay, so again, what is X dot then? X is defined in that picture. X is the X coordinate of the moving point. So what is X dot? What do you think, Jonathan? Okay, yeah, okay, good. It's the rate of change of the motion of that point in the X direction, right? So we've kind of broken this down. There's really two parts to the motion of this point. And if you're in physics, this will probably be a little easier to understand. But we could say that the velocity of this point has two components. It has an x component of the velocity, right? And that's really all x dot is. It's the rate of change of x. That's dx dt. Well, that's the speed or the velocity of this point in the x direction. Y dot would then be the rate of change of the y coordinate. So that's like the y component of velocity. And if you combine those together, you'd get the overall velocity, right? Now, we could talk about that in terms of vectors. I don't want to get too bogged down by the vector stuff right now. Here's a way you could kind of visualize this. If I wanted to sort of isolate x dot, I could take a perspective where I'm up here looking straight down on this thing from high above. If I'm looking straight down on this whole contraption from way up high above, what would I see? Well, as the point moves along this wire, I'm only going to see the horizontal movement of that bead if I'm up above, right? I don't see the vertical motion. Everybody get that? Okay, so that's what I would be isolating if I were looking from up above straight down on this thing. I would be looking at x dot. Okay, how would I kind of isolate y dot, or the y component of the velocity? Where would I look from there? Well, I mean, if I want to see the y component, right? Y is the vertical variable, right? So I'm looking at the, yeah, if I looked from over here, if I watch this thing as the bead slides along, then I wouldn't really see the horizontal component, right? All I would see looking from this perspective is the vertical component of the motion. And I'd be looking at, as I looked and I measured how fast this thing were moving vertically, that would be a measurement of y dot. Everybody see that? Okay. All right, so we've got some information here then. We know, that's really all we know, isn't it? We know that x dot equals 2. Let's write this in terms of dots, how about? So x dot equals positive 2. And we're looking for s dot, aren't we? ds dt? Okay. Well, what's my parent equation going to be? What's the distance equation here? Because s is distance, isn't it? Right? Okay. Yeah, distance is just the square root of the change in x squared and the change in y squared, right? I could make a right triangle out of this if I wanted to. Here's my right triangle. I could go, right? There's s. Well, what's this distance going to be here? The original x position is 0. The x position at this snapshot is x. So x minus 0 is just x. Everybody agree? Okay. That's the length of the horizontal leg of this right triangle. What's the length of the vertical leg? Y. Yeah, I've got this y value minus this y value is y minus 0. So I get that right triangle. Okay. So then by definition, my parent equation, S, I'm not even going to involve square roots, right? I'm just going to use Pythagorean theorem. To me, the distance formula is nothing more than the Pythagorean theorem, right? That's all it ever is. So S squared equals what by that right triangle? Yeah, x squared plus y squared, right? So there's my parent equation, okay? What's my output variable of that parent equation? What am I calculating from the parent equation? Distance, S. What are my input variables? X and Y. Okay, so I got 2 of them, right? That's a little bit inconvenient because the next step in related rates, think what we've done here. Step 1 was we identified our snapshot values, right? Step 2 was we came up with a parent equation. What's step 3? Yeah, I'm going to differentiate implicitly with respect to t because I want to get dots. I want to get an x dot and an s dot popping out of this equation so I can solve for s dot, right? Everybody agree? Okay, what's the problem there though? When I differentiate this thing with respect to t, what's the derivative of s squared with respect to t? Yeah, 2s s dot, right? The derivative of hand squared is 2 hand times the derivative of derivative of s with respect to t is s dot, right? So this is giving me 2s s dot equals the derivative of x squared 2x x dot plus 2y y dot. Yeah. Okay, well, let's see. What information could we plug in there? I'm trying to find s dot. Which of this stuff could I check off? Well, I know the value of x dot, right? Okay, so I know that one. I don't know x, do I? Right, I don't know x. You know, I probably need to pick a point here on this graph too. I'm going to do that. Let's pick the point. I'm going to say this. When x equals, let's say when x equals 2. Yeah. Okay. So now I know a value of x, right? I'm trying to find s dot, so that makes sense. But that leaves me with some stuff that I don't know, doesn't it? I don't know s, I don't know y, and I don't know y dot. What are my options? Remember that step 1, my snapshot values, I can always go back and add to that list if necessary, right? What do you think, Jonathan? You have an idea?
I don't know if this is possible, but can we take the derivative of like y equals x squared plus 1 to change that into y dot?
You could. You absolutely could. One thing we could do is we could say, okay, we know what y is in terms of x. We could differentiate this implicitly with respect to t and get y dot equals some, 2x x dot. I can do that. Okay, and in some cases I might need to. If they were asking information about y, I definitely need to do that. Now they're not this time though, are they? It's a very good idea. And it's a road that we definitely could take here, a route we could take. They're really just wanting us to find s dot though. Okay. Is there a way, what's inconvenient about this is my parent equation involved two separate input variables. It's always preferable if we can trim that down to a single input variable if possible. So we have a function of only one variable instead of a function of two variables. This is really s of x and y, right? Does anybody see a way to do that? How I could rewrite that parent equation in a more simple way where I've only got x's involved in my function, not y's. Right? This is just in general, this is the definition of distance. What do you think? Ah, sure. Yeah, look, we know the specific function that this is sliding on, don't we? It's sliding on this function right here. That's defining y in terms of x. We call that a secondary equation. That's giving us some additional information that relates x and y. So why not just make a substitution? I could plug that in for y, couldn't I? Right? That's giving us a better parent equation. So then we could kind of get rid of this whole idea here. And instead, we're going to replace this with the new parent equation, s squared equals x squared plus the quantity x squared plus 1 squared. Now, that may not look better, but it is, right? Because now I've only got one input variable instead of two. And we can simplify that. If I square out the quantity x squared plus 1 and combine like terms, I'm just going to have some polynomial, aren't I? Okay, so let's clean that up a little bit first. If I square this out, what am I going to get? x to the fourth, so that's going to be my first term, plus 2x squared, which I'll add another x squared to that and get 3x squared, plus 1. Okay, good? Way better. Okay, way better. And so now if I differentiate implicitly, I'm going to get 2s dot equals, what's that term going to give me? 4x cubed x dot plus 6x x dot. And look, I could factor an x dot out of that side, couldn't I? Everybody agree? Okay. So anything else I could do there just to clean things up a little bit? Yeah, I could just divide both sides by 2. Okay. So let's do that also. And that's going to give me s dot equals 2x cubed plus 3x times x dot, right? And I'm trying to find s dot. Well, now look, I've got all that stuff just about, right? I know x is 2. I know x dot is 2, right? So that's everything. What's the only thing I'm missing here? Missing s, okay? What can I do about that? What could I do about that? So what could I do? Yeah, I've got a snapshot, right? I've got a snapshot that's one frame in this video, okay? This is our general picture where we involve the variables, but at that one snapshot, what does this triangle actually look like? In my snapshot, I know that the x value is 2, correct? So that length is 2. The y value is going to be 2 squared plus 1, so that's 5, right? Okay. So I could calculate the value of that hypotenuse, which is s. Yes. I just made it up. I wanted to change the problem. This problem had a little error. In order for this one, our answer was going to be written in terms of x's and y's, which I just didn't want to do that to you. It doesn't seem like that's not necessary at this point. So I cheated and added that additional information that I think initially I meant to put on there anyway, something like that, and I just forgot to. Okay. Okay, so then what's the hypotenuse? Square root of 29. Good. Everybody get that? Okay. So one thing we could do is we could just go up to our list of snapshot values and add s is the square root of 29, and now we got everything. Okay. The other option would have been we didn't really have to do this stuff right here if we didn't want to. We could have said, okay, well, s dot is equal to all this stuff divided by s. But what is s? Well, s is defined right here, isn't it? S is just the square root of x to the fourth plus 3x squared plus 1, right? So we could have done something like that. Okay? And guaranteed, that's going to give us, if I plug in 2, I'm going to get a square root of 29, right? I'm going to get what? 16 plus 12 is 28 plus 1 is 29, right? So I could have just written s dot, I could have rewritten it in terms of just x's and x dots, and then I wouldn't have even had to include that extra value. They mean the same thing pretty much, don't they? Just one or the other. Personally, I like this way better. I always prefer to just add as few values to the snapshot list as possible, right? It just seems more mathematical to me to do it this way, right? It's just more basic, okay? But now all I have to do is plug and chug, and I got it. So S dot equals, we said X was 2 and X dot was 2, right? So this is just going to give me 2 times 2 cubed, that's, what's that, 16, plus 2 times 3 is 6, times X dot is 2, divided by, we already know that's the square root of 29. So what are we getting here? 22 times 2, 44. What should my units be? Did we have units up here? They didn't even give us units. So it's just going to be, the S dot is just going to be whatever we're measuring this in, units per second. Okay? Maybe it's centimeters and seconds, who knows? We didn't specify. Okay? Did we specify? Oh, we did, centimeters and seconds. Yeah, we did. Never mind. So it's going to be centimeters per second then, isn't it? Right? We're measuring a distance per time. Okay? All right, give me 1 to 5. How are we doing on that? Okay? It just takes hammering through problems on this stuff. All right, we're probably not going to get through this one, but I want to look at one more like that where we're going to eliminate a variable. Okay, so this is a pretty standard. Here's our set of, again, just our list of steps in related rates problems. Okay, let's look at one like this. If we get through this one or not, but this is pretty common. So at a sand and gravel plant, sand is falling off a conveyor onto a conical pile at a rate of 10 cubic feet per minute. Okay, so it's giving us our units here. Distances are measured in feet. Time is measured in minutes. Okay. The diameter of the base of the cone is approximately 3 times the altitude. At what rate is the height of the pile changing when the pile is 15 feet high? So the shape stays the same. It stays a cone, right? It's dropping the sand on the top of this conical pile, and the sand kind of sloughs off down the sides, and it continues to just grow, but it stays a cone with the same aspect ratio, right? It just like it's getting dilated, right? The cone is just getting dilated up, so it's getting bigger and bigger, but it looks the same shape, okay? All right, so here's a picture. Everybody agree that kind of makes sense as our picture then? Okay, and we want to assign some variables to this. Well, let's go ahead and say that the radius of the pile we'll call X, and the altitude or the height we'll call Y. Okay? Can't remember what that is. What's that telling? Oh yeah, and that's just a quick reminder that the volume of a cone is 1/3 pi r squared h. How do you remember that? The volume, like if I were to take the volume of a cylinder of radius r and height h, is just pi r squared h, right? Okay. Well, if I were to start with a cylinder like a candle, and I were to carve out, I were to cut everything away, so all I was left with was just a pointy cone with the same base as the cylinder. Turns out that I've carved away 2/3 of the volume, and I've left 1/3 of the volume of the cylinder. Okay, so a right circular cone has 1/3 the volume of the cylinder that you create it from. Okay. What do? We have to identify snapshot values. Give me a snapshot value. Tori, give me one snapshot value here. We're just looking for numbers up here, right?
10 cubic feet.
Okay, what is that?
That's the rate.
Okay, so what quantity though? It's going to be a dot, isn't it? Because it's a rate. Yeah, it's V dot, isn't it? Right? How do you know? Well, the easiest way to know is look at the units. Look at the units. We have 10 cubic feet per minute. Well, what cubic feet is a measurement of what? Volume. Yeah. So we're looking at volume per time. So that's a V dot, isn't it? Rate of change of volume per time. So there's one thing we know right away. We know V dot equals positive 10 in our units. Okay. What else do we know? 15 feet. Yeah, we want to know our snapshot is defined by the time when the pile has a height of 15 feet. So we called that y, didn't we? So y equals 15. What are we trying to find? H dot, right? That makes sense? Because well, H dot, but what do we call it? Y dot, right? The height is, we're calling the height Y. Okay. So at what rate is the height of the pile changing? So we're looking for Y dot. Okay. Well, next step is we need our parent equation, right? Okay, what's our parent equation? Volume of cone. Only in our case, it's going to be X's and Y's, right? Instead of R's and H's. Okay. How did I arrange this? Yeah, parent equation. So there it is. Okay, our parent equation is going to be V equals 1/3 pi x squared y. Okay, got it? Now we got a parent equation. What do we do? Differentiate, right? We got to get dots out of this. So I'm differentiating, Pagan, what am I differentiating both sides with respect to? Okay, well let's go back and let's talk through this again. You guys ask me questions when we're going through this. If something's not making sense, stop me and we'll talk more about it. First step, identify snapshot values. Okay, well those are the things that are given to us. Give me 1 to 5 on snapshot values. How are we doing on that? Okay. Okay, the hang up comes with the parent equation. Well, how about the parent equation? Does that make sense? Any questions on the parent equation? How do we know what the parent equation is? What's the job of the parent equation? How does the parent equation relate to what I've written down here for my snapshot values? It's got to relate them together, right? The parent equation, though, it's going to be a static equation. It's not going to involve rates, right? It's going to be a static equation that involves all of the static variables. So we're going to ignore the dots. It looks like I've got V's and Y's, right? So I need an equation that's going to relate the volume of this cone to its height. Well, that's the volume equation, isn't it? Right? That's our parent equation. Okay? So now think what the strategy is here. We've got this parent equation that relates these variables, but this, what we want to come up with here, we're trying to solve for Y dot, and I have information about V dot, right? So the information I have does not fit a static pre-calculus equation like that. It fits a calculus equation. It fits a derivative. Whenever we see derivatives, we know we're talking about rates, right? So my goal then is, how am I going to get from my parent equation to a related rates equation? I need to turn this into an equation that involves rates of change. So I know I'm differentiating to get derivatives, but what am I differentiating with respect to? Because derivatives, we always have to know, what are we differentiating with respect to, right? Back in the good old days, before related rates and implicit differentiation, we pretty much always differentiated with respect to x, right? We had functions of x and we took derivatives with respect to x. But lately, we've been doing some different stuff. We've been differentiating with respect to other variables, and this is a physical system. Think about, what's our input variable almost always for a physical system? If we want to watch it change, we're interested in how it changes with what? Time. Yeah, we want to know with time, how is this thing changing, right? As time passes, sand is being dumped onto this pile and it's growing. So I want to know, how are these quantities changing with time? So I've got to implicitly differentiate with respect to t, because I've got these dots here. Okay? Question, comment? Okay, we might have to, right? We might have to go back and add a snapshot with the height then too, right?
Or no, I mean the diameter actually. The diameter is 3 times the height always, so the diameter would be 45.
Yeah, you're right. So the diameter would be 45, right? Agreed? Okay. Right. Didn't it say that diameter's 3 times? Is that what it said? Diameter's 3? Yeah, I think it said something like that, didn't it? Right. So we could potentially add some more stuff to that snapshot list, right? But we need to know what stuff is going to be necessary for us to have, right? So here's our parent equation. If I differentiate with respect to t, what am I going to get? Okay, what's that going to give me for my, I almost want to see something here. Okay. What is this? Oops. Give me just a second here. Oh, never mind. Yeah, okay. Yeah, I remember what I was doing here. Okay. I did all this stuff before break, so I'm trying to remember what I was thinking. Okay, so now we've got to find a related rates equation. So we're going to implicitly differentiate with respect to t. So what's the derivative of v with respect to t? Okay, v dot. Okay, how about this? The 1/3 pi we can just leave out front. That's a constant, right? So Pagan, what's the derivative of x squared with respect to t? Good, 2x x dot. So I'm getting 1/3 pi, but I've got a product here, don't I? Right? I've got to use the product rule. The derivative of x squared times y with respect to anything, right, follows the product rule. So I'm doing, actually, let's do this. The way we usually do this is first times derivative of the second plus second times derivative of the first, right? That's how, it doesn't matter. So I will do the first one, x squared times the derivative of y, which is what, everybody? Y dot, plus the second times the derivative of the first, which is, I've already been told, 2x x dot. Right? And I'm trying to find y dot. Well, this is what Max was talking about. Look, if I'm going to solve for y dot, I've got to be able to plug in values for all of the variables and rates, right? Well, I know v dot. I know x dot. Do I know? Oh, sorry, I don't. I know y. That's all I know is v dot and y. So I know that term or that factor and that factor, and that's it. I would have to go back and find the values of x and x dot to be able to solve for y dot, right? Could I do that? I could, right? I could go back and I could look at this picture up here at this snapshot and say, okay, well, I know if the height is 15 and the diameter of the base is 3 times the altitude, so that's going to be 45, I could come up with a value of x, then that would be 45 halves, right? And I could plug all that stuff in, but I've still kind of got a little bit of a problem then with my x dot and my y dot. I could make all this stuff work, but does anybody see a better way to do this? If we're going to jump down this rabbit hole, I'm going to claim that we have taken, it's going to work, but it's not the best way. That's kind of a wrong turn. Could we have done this a little bit more easily? Could we have done this a little more easily? What's making this difficult? All the different variables, right? What makes this difficult is the same issue we ran into last time. I've got volume as a function of x and y. I'm really only ever asked about y. I'm given information about y and asked about y dot. So wouldn't it be more convenient if I could write volume as a function of what? Just y. Is there a way I can do that? I would need some secondary equation to be able to make a substitution here. My goal would be able to substitute for x, right? Something for x and get rid of the x's. Is there a statement up here in my original problem that would allow me to do that will allow me to come up with a secondary equation.
Because the diameter is 3 times.
Ah, yeah, look at that, right? If the diameter of the base of the cone is 3 times the altitude, what's that telling me? The diameter is what in terms of my variables? Well, okay, but the diameter, as it's written right here, diameter equals true. But what's I don't have any D's.
Oh, you want X?
Yeah, I want X, don't I, right? Diameter is just 2X, right? Because X is my radius. So the diameter of the base, that's 2X, means equals 3 times the altitude. What's 3 times the altitude? 3y. Well, look, there's an equation, right? There's an equation that relates x's and y's. So if I solve that for x, x just equals 3/2 y. And look what I can do. I can make a substitution then. I can substitute that right in there. Okay. And if I do that, life's going to be a lot better, isn't it? Then I'm going to end up with the new equation, v of y is equal to 1/3 pi times the quantity x squared. Well, that's just 3/2 y. Times y. Way better, right? If I square out the quantity 3/2 y, that's just giving me what? 9/4 y squared times another y would be a y cubed. Okay, so then I'm getting volume as a function of y equals pi thirds times 9/4 y cubed. And I could cross cancel and make that a 3 on top. And so I end up with a much easier way to do this now. I've got volume as a function of y equals 3 pi over 4 times y cubed. That took a little bit of doing, but wow, the calculus is going to be way easier now, isn't it? Yes, sir.
So when you're gonna differentiate
Mhm.
the parent equation, you want only one out.
You really want to try. There may be some instances where you just can't do that. But if you have enough information, you always want to pare this down to only the necessary variables. Okay? Question, comment?
Yeah, how did you go from V dot to V of Y? Like, just what does that mean?
I didn't go from so we've said, yeah, this is a wrong turn. We're not doing that, right? We're going back and recreating our parent function in step 2 so that it's easier to do the rest of the problem. Now, when we differentiate with respect to t, we don't have to use that darn product rule anymore, right? Now it becomes a much easier problem when we differentiate this guy. We just get v dot equals 3 times 3/4 pi is 9/4 pi y squared y dot. Okay, that's all good. That's all stuff I know, isn't it? So now when I solve for y dot, I just get, what am I going to get? If I isolate y dot, I'm going to get the 4 on top. So 4 v dot divided by 9 pi y squared. Everybody buy that? I divide by y squared and multiply each side by the reciprocal of that fraction to isolate y dot. Okay, and those are things I can plug in. Y dot or v dot was what, 10? Is that what it was? Yep, 10 in our units. And y was 15? No, what was it? Was it 15? 15 feet high, right, okay. So there's my answer, right? It's just a number. So that gives me 40 over 15 squared, 225 times 9. What the heck's that going to be? 1,800 plus 225, so 2,025. Something like that, right? What would my units be? I might have made an arithmetic mistake there. But I'm measuring y dot, so it's a height. What would the units of height be? Feet, and it's a dot, so per, what are we measuring in per minute? Looks like we're measuring time in minutes, okay? So, hope did I do that right? Is that what you got? Okay. Okay. Make sense? You guys probably need a day to work on this stuff now and get some questions answered. Okay.